Well, good morning, everyone. My name is Sarah Spurgeon. I'm a professor of control engineering here at UCL, but I have the great privilege to be one of the leads of the UCL Robotics Institute. And on behalf of all colleagues here at UCL, I want to really welcome our guests. We have such a rich program and such a diversity of attendees for this inaugural in-person event that we're sure that the day is going to be absolutely wonderful. Internally, robotics is spread across UCL. There are so many interesting technologies and interesting applications that it's really hard to get us all together. So for the UCL family, this is a great celebration. It's an opportunity to get to know and see each other, and particularly to get to know some of the students. But we're really delighted that more than a quarter of the attendees today have come from industry, and also we see academic colleagues and their students from other institutions. So we're really pleased to be able to interact with you, to learn from you, and to help build the UK robotics community. So without further ado, I'm going to hand over to Helga, who is going to introduce our first keynote speaker. So thank you all very much.
Thank you very much, Sarah, and thank you very much, Machi, for introducing and for giving us a short overview over today. Sarah already mentioned that we have about 25% of industrial visitors today, so I thank everyone for coming today. And I'm also pleased to announce that our first speaker will be from industry, and it will be Robert Skilton. Robert Skilton is Head of Research at RACE at the UK Atomic Energy Authority. He is crucially and deeply involved in fusion robotics programs in the UK and internationally. And today, I'm sure he will give us an overview of his experience over the 10 past years that he has been involved and about the future. So please welcome Robert Skilton.
Thank you. Just firstly, thanks to the organising team for inviting me to speak here. This is really a privilege, so thank you very much, and especially to Machi for the coordination prior to the event. Let me just get my slides up. 1 second. So while those are hopefully loading, there we go. Okay. So, yes, my name is Robert Skilton. I'm the Robotics Fellow at UK AEA, which means I head up the robotics research programs for the UK Atomic Energy Authority. UK AEA is a fusion energy research lab, so its primary focus is on delivering fusion energy, which is the future low-carbon energy source for future generations. Fusion is really exciting, but it's also really difficult, and there are lots of challenges that we need to solve to get there. And a lot of those challenges relate to robotics, which is why my organization, RACE, exists. And we have around 350 people working on the robotics challenges of fusion energy, which is something that I want to excite you all about, hopefully. This is JET. So this is a fusion reactor. It's one of the world's biggest and most powerful fusion reactors. And it's just here in Oxfordshire, only a few kilometers away from here. As you can see, because of the hazardous environment that exists, because of radiation and other hazards, it's historically been upgraded and maintained over 25 plus years using robotic systems. And because of this, we have developed a whole range of technologies and capabilities in UK AEA for robotics in extreme environments. This includes technologies like long-reach robots. You can see here an example of a boom robot, which is roughly 10 meters long, and it's designed to go into radioactive environments. through narrow entry ports on the side of pressure vessels. And this is a recurring theme we see where we have to access through long reach distances, through narrow ports. We also make extensive use of digital technologies, and we've been using virtual reality technologies since about 1991, which have been used to support training, development of tasks, and live execution of tasks in real time for these robotic operations, which are very complex and need to be right on the day. And those technologies are all brought together to be operated by teams of expert robotic operators who operate from control rooms like this, where we bring together all of the technologies for remote operation of the robotic systems, using camera views, digital software and visualizations, but also haptics, so the operators can feel what's going on in the remote environment as well as see what's going on. So this is the basis of what we've been doing, and this is where our expertise has grown over the past 25 years or so. And what I'm going to talk about is how that is being reused and redeployed in other areas outside Fusion, and where some of these pieces of work are having wider impact and benefit on society. Who can tell me where this is? It's Fukushima. And this is specifically March 11th, 2011. I remember that date well because it's my birthday. On this day, there was an earthquake off the coast of Japan with a subsequent tsunami, which caused one of the world's worst nuclear disasters. It's really bad. And it's resulted in hydrogen explosions and meltdowns occurring in the reactor buildings, which have left unknown but very hazardous situations which need to be cleaned up and remedied. So TEPCO, the company that was responsible for operating those functional power plants at the time, suddenly became responsible for a very different task, which was how do you clean up one of the world's worst nuclear disasters? And we started having conversations about things like how do you reshape the teams that exist and develop new skills to be able to deal with these types of operations. We don't know what's going on inside a lot of those buildings because we don't have the data and we can't access the buildings. So how do we gather data to make better and more well-informed decisions about how to approach those problems? How do we de-risk and reduce the cost of these long decommissioning operations, which will take decades? And also, how do you create a marketplace where you can go off and buy a fuel debris retrieval machine or whatever it is you need to do the decommissioning task? And we came to a program idea which starts to explore some of these challenges. And it's called LongOps. This is a UK-Japan collaboration on research and development for de-risking long-term decommissioning operations using long-reach manipulators. And a large chunk of it is based around this idea of the digital tools and digital mock-ups. But as you'll see, it's exploring a wide range of areas. And I'm going to go through some of these, some of the 5 main themes that are present in this program. So the first question we wanted to answer is, how do we simultaneously build capability in this new team to do robotic decommissioning operations whilst also building capability to bring in and make use of digital tools and digital twins to help with the decommissioning operations? So this is a piece of software that we've developed at UKAEA. It's called Rover. And it's based on games engine technology. It's based on the Unreal Engine. I'm sure lots of you are familiar with it. But it's got years' worth of development and effort gone into it explicitly for the purpose of supporting teams doing remote robotic operations. So it's packed with features that help with those sorts of things. And this is used for, as I mentioned before, training operators. It's used for rehearsing tasks in advance to make sure that they're going to go as we think they are. And then it's used for supporting live operations in real time with feedback from the environment to provide additional information and additional views. And it's set up so the environments can be rapidly changed, and we have here an example of a mock-up of some of the environments inside the Fukushima reactor buildings. And that's been used in training. So you can see here some of the TEPCO team we've had brought over to the UK, and they've been spending months or years with us working together with our teams to understand how these technologies can be used, and developed their own mock-ups of Fukushima Daiichi, and it's been used in assessing some of the concepts that we've been exploring for decommissioning. Now, it's all well and good having these digital tools, but if you want to be able to buy digital tools like this and support them over decades-long operations, you need to be able to bring together pieces from different suppliers and have them work together. And you also need to be able to flexibly adapt to the changing environment and changing situation as the situation emerges and evolves over time. So our second theme focused on this challenge, and it was about interoperability, and focused on how you could rapidly integrate different robotic devices and different software elements so that they work together seamlessly in a plug-and-play manner, and also allow this kind of level of operational agility, and allows things like standardized user interfaces, which minimizes training duration. This is actually a video from 2016, so this is very old. But it shows a really good demonstration of integrating lots of different types of robotic devices in a real remote operation. And we've extended this concept to the idea of integrating digital twins and digital mock-ups in an interoperable way, and developed capability with the TEPCO team on how to operate and develop these types of tools, how to integrate these systems, but then also how to work with industry to buy these types of tools in a way that is going to meet your needs, how to be an intelligent customer. The third theme is on manipulation and how you develop and deliver robotic tools for doing the physical tasks that are present in the environment. You can see here in the picture, this is actually a robot called Mascot. This is something that I spent 5 years personally working on and developing, so I feel very close to this. And it is, as far as I'm aware, one of the world's best performing haptic telemanipulator robots. It's a really special machine. One of the things that we've been up to over the past 5 years or so is developing the concept of manipulation further, and looking at how off-the-shelf robots, cobots, can be used for teleoperation, but also autonomous manipulation, autonomous grasping and handling in delicate, confined spaces like nuclear decommissioning glove boxes. This is a piece of work that we did with the RAIN Hub, which was led by Barry Lennox at the University of Manchester, and it was a really cool piece of work, which is now continuing into what I'm describing. So we took these ideas and that learning and worked with the TEPCO team to both assess the performance. So we've developed standardized methods of assessing the performance of manipulation tasks, and use that to determine the performance of various manipulators, both in training and in procurement situations. So the question we're trying to answer here and help others answer is, if you have a really difficult remote robotic task to do you need the £10 million manipulator, or can you get away with the £100,000 manipulator? Because that's a really big difference. So we've been exploring those and trying to answer those questions, but not entirely there yet. Another aspect of what we're doing here is looking at how you train for remote manipulation operations. So bringing the digital world into training again, and looking at how you can bring haptics in. And this is a company called UCL Robotics that we're working with here, who are doing amazing work in surgical skills training, and exploring how these technologies can be translated into the nuclear industry to train people on nuclear manipulator systems without having to have access to those systems, which are typically expensive and hard to get hold of. The fourth theme is on de-risking long-reach robotics. So I mentioned before the need to access through narrow ports over long distances. In TEPCO, some of the fuel debris retrieval concepts look at 20-meter long side entry manipulators. So you can imagine how difficult that is. With long reach manipulators, we typically have flexible deformation, which has to be dealt with, as well as vibrations. And these are problematic when you don't want to collide with your environment. So we've done a lot of research, and you can see some of the videos here of examples of work we've done on modeling, measuring, and counteracting the flexible deformations and vibrations using control methods. And again, taking these concepts over to Japan. This is at the Naraha facility near Fukushima, working with the TEPCO team to train on how to use long-reach manipulators in the context of vibration and flexible deformation. And this is some of the work that UCL is actually helping us with. The fifth and final theme that I wanted to talk about is how do we get data from the environment so that we can make those decisions better and better plan the decommissioning operations. That was the wrong button. So back to the Rain Hub. We worked very thoroughly with a lot of universities in that, but in this particular case, this is work led by the Oxford Robotics Institute, Nick Hoare's group at Oxford. And we were working on mobile robots for inspection of fusion facilities and nuclear waste facilities. So this is things like drum stores, but also fusion reactor buildings. We also worked in collaboration with the Republic of Korea on things like remote live 3D reconstruction. So this is about teleoperation over narrow bandwidth connections like the internet. And how do you prioritize intelligently the data that's being sent back to the operator so they can have the information that's required to do the task as a priority over any other information. And through these programs, we've worked extensively with industry and managed to successfully spin out and commercialize some of the work, including supporting a spin out from the University of Oxford, NavLive, you can look them up, as well as helping companies take their first steps in new industries and taking steps in the nuclear industry. I'm just going to finish with this one point. So firstly, I think this is an amazing video. Throughout the Rain Hub, we progressively did research, and we wouldn't stop at research. We had to progress that towards demonstration on sites in front of customers in realistic environments. And some of these took years. Some of these took more than 10 years to get into these hazardous sites. What I think the biggest impact we've had overall through these programs is changing perspectives of the site operators and the regulators on what is possible and what risks are worth taking in terms of bringing new technologies and robotics into these hazardous environments so that they can have benefits. And what we're seeing is that now we're starting to get these demonstrations going. We're being invited back again and again to do more and more tasks in these environments. So that's a brief summary of some of the work that we've been doing, in particular with Japan. I'm very keen to attract all of you to work on fusion problems. They're all still open. There are lots of problems left to solve. We're in the process of producing a document which summarizes the top challenges of fusion energy for robotics, which I'll share with you. In the meantime, please feel free to come and talk to me. I'm here all day, but get in contact if you want to talk about fusion robotics. Thank you very much.
Thank you very much, Rob, and thank you very much for sharing this fascinating work, how you're pushing the maturity of these robotic systems into real applications. And you spoke about many challenges, actually, in robotics. You spoke about the control and dynamics issues that you had, manipulation, still an unsolved problem, sensing, haptic feedback, teleoperation, etc., and also about digital twins. So digital twins you have been working for many years on this. They are coming up again or still growing. So what do you think are the biggest challenges in developing digital twins for these complex robotic systems that you have developed and putting them into practice?
Yeah, it's a really good question. And fundamentally, I think it comes back to the end users and the people who are going to be using these tools. And clearly understanding what it is that is going to be useful to them. I've seen a lot of work through universities and a lot of work that we've personally done in researching and developing technologies that have then not been used because they weren't actually what was required in the first place. So I now encourage in all the research activities that I'm involved in, embedding expert operators, people who have done the tasks, into the research teams so that they can impart their experience on what it is that's going on. So I would say that's one of the biggest challenges, but overall there are numerous challenges. I'd say another big challenge is the interoperability challenge and the ways of organizing data. So if, again, we want to get to the situation where ideally we're not locked into one single supplier or one single technology, and we want to be able to take pieces like Lego bricks and put them together. How do you organize data so that that's possible in a digital twin context? I have no idea, but if anyone wants to help me with that, please come and talk.
Yeah, anyone wants to help or has a question right now? So please.
Very nice talk. I have a question about digital twin. So I've done the research, similar research before, and I find it's very important to run both the control software and the physics simulation ahead of time to rehearse it. So wondering, in the green ghost you have shown, did you run both the control software and the physics ahead of time? Or it's just graphic display?
So the green ghost, as you correctly called it, in that in the video you saw, is simulating kinematics, and it's simulating the geometry and control system of the robot. So it's simulating the response of the control system of the robot to the commands that are being sent. It's not simulating dynamics, and it's not simulating integration with the environment. The work we're doing with the haptics that you saw is kind of one of the first steps in bringing more physical simulation into that environment, but we're not there yet. Other people probably are.
Any further question? There's one up there. Might be a haptics question.
It's more robotics, actually. Well, thank you very much for the talk. I saw a lot of robots there working together with the workers. I wonder what is the progress regarding sustainability of the robots? So when they stop working, so then what happened to them?
It's a really big challenge, and it's something that's really important to solve. So for fusion reactors, we want to be able to recycle and reuse all components, not just the tokamak components, not just the reactor components, but also the maintenance systems, which make up a big part of that. So we're very interested in the concepts of robots maintaining robots, which means one of the things that we're working on in our research program at the moment is non-destructive disassembly, decontamination, and maintenance for reuse. So that is a really important thing that I think we need to solve. Because, further to that, when you get contaminated waste, it's very expensive to deal with and dispose of. And if your 5-ton robot becomes contaminated waste in that category, that's the situation you don't want to have to deal with. So you want to minimize that as much as possible. So decontamination, reuse, recycling, those things are really important.
So thank you very much. Rob, you will be staying here for
I'll be here
morning?
all day. So
all day,
if anyone wants to talk to me, come and find me.
That's fantastic. And let's thank our speaker again. So before everyone is running for the coffee break, as Machi explained, there are some demonstration and posters downstairs. This will be until 11:15, and at 11:15 we will have parallel sessions, 2 of them. One will be in this room, chaired by Sophia, and in the other room by Tom, Jeremy Betham room downstairs, I believe it is. So please make your way at 11:15 for the 2 parallel sessions. Thank you very much, and see you later.